Okay. Oh, well, I messed up there. Well, good. Okay, so today we're going to pick up where we left off yesterday, and we were factoring. Today we're going to look at a shortcut. Factoring when A is equal to 1. We have a little shortcut when A is equal to 1. And here's an example. When A is equal to 1, as in this problem, there's an understood 1 here. There is no need to multiply first times last, get negative 13, do all your stuff, and then come back and divide by 1. Because multiplying by 1 changes nothing, divided by 1 changes nothing. So what we can do, we can skip a bunch of steps when there's an understood 1 in front. You can just put X and X, and then figure out what multiplies to the last number and adds to the middle number. So in this case, the only things that multiply to negative 13 are 1 and 13, and we know that since it's negative, one of them needs to be negative. The 12 is negative, so we're going to make the bigger number negative.
What does that say above 12?
Positive 1, negative 13. Above 12, X, it says adds. So it's got to multiply to the last number, add to the middle. 1 times negative 13 is negative 13. 1 plus negative 13 is negative 12. If you wanted to check this, how could you check this? Foil it. Foiling is reverse factoring. Factoring is reverse foiling. Okay, they undo each other. All right, let's see if y'all can do problem 2 by yourself. This is problem 2. X squared minus 10x plus 21. All right, people that are watching this video, we did this one for a practice problem and got this answer. There's one more special method we're going to look at, and it's when you have 2 terms. And it's just ax squared minus c. There's no middle term. And it's a very special case of ax squared minus c called difference of squares. And so what it really looks like is a squared minus b squared. But I don't want to call it that. But I'm going to have to. And what we see when we're factoring a squared minus b squared, they're a difference of squares. The first term is a perfect square, like 25, 36, 81, 4. Things you can take a square root of. Is 10 a perfect square? No. What's the square root of 10? It's some kind of decimal. Okay, so 10 is not a perfect square, but both of these have to be perfect squares, and it has to be a difference. We can factor that like this. A squared minus b squared factors into a plus b times a minus b. You take the square root of the first one, the square root of the second one, use both of those factors in each of the factors, and then make one of them positive, one of them negative. And I want to show you why that works. If we FOIL this out, we get a squared minus ab plus ab minus b squared. And look what happens with the outer and the inner. Minus ab plus ab cancels out, and you have a squared minus b squared. That's how difference of squares works. So when are we going to use difference of squares? When there's no b term. In your original problem, there's no b term, no linear term. That's when we're going to use difference of squares. All right, so let's do an example with difference of squares. So our next type of special case is difference of squares. Here are our examples. We have x squared minus 100. X squared is a perfect square. What's the square root of x squared? X. So you're going to start each one of them with x. 100 is a perfect square. What is the square root of 100? 10. And then you're going to finish it off by putting plus, minus. By putting the plus and minus, we guarantee that those middle terms will cancel out. And you just get x squared minus 100 when you FOIL. All right, so let's look at the next one. This looks a little more complicated, but really it's just as simple. So we set up our factors. 9y squared is a perfect square. Terry, what's the square root of 9y squared? 3y. The square root of 9 is 3, and the square root of y squared is y. Good. All right. 25z squared. Sorry, not z squared. Z to the 6th. Who thinks they can tell me the square root of that? Yes? 5z to the 3rd. And then you put a plus and a minus. With this exponent of 6, fell off my stool. With this exponent of 6, to take the square root, you're going to divide 6 by 2. You're saying, how many groups of 2 z's do I have? I have 3 groups of 2 z's. And they're factored. Any questions? Let me pause it real quick. Cover with factoring, the last thing I'm going to cover is what to do, like how to put it all together. So our examples here, the directions will just be factor. And I have, where's my problem? -2 x squared y minus 4xy plus 30y. And then I have 5x squared minus 20. We need to figure out how to factor these. So looking at your chart, what is the first step in every factoring problem? GCF. So I look at this. What is the GCF of 2, 4, and 30? 2. Do they all have an X? Do they all have a Y?
Yes.
Yes. Now remember our note from yesterday, if the leading term is negative, we're going to factor out a negative. So put your GCF on the outside of the parentheses, along with that negative, and then we're going to factor out that negative. So it helps me to write it up under here. You don't have to. But that leaves me with x squared plus 2x minus 15. When I factor out the negative 2y, I get x squared plus 2x minus 15.
Kind of just a step I took on homework.
Okay.
I just like
We've taken out the GCF of negative 2y. How many terms are left? 3. Is the A 1 or not 1? It's 1. So we're going to do the shortcut where we put x and x. And we say what multiplies to negative 15 and adds to 2. The only things that multiply to 15 are 1 and 15, 3 and 5. So which pair are we going to use? We're going to use 3 and 5, but because it's a negative 15, one of them needs to be negative. The 3 needs to be negative. Whatever this middle number is, that's what the bigger number is going to be. Okay? And then we can't forget this negative 2y that was our GCF. We have to include it as part of our answer. Now at the bottom of your little pink flow chart, it says, include the GCF in your answer. So it's a reminder to do that. And make sure to check that no part of your answer can be factored further. Do either of these have a GCF? Are they difference of squares because they're two terms? They're not. So we're done. That's it. All right, looking at the second example. All right, so we've got the GCF as part of our answer. Neither of these can be factored further, so we're done. The next section that we look at, we're going to take it one step further and use these factors to help us find zeros of the function. And that's what your coloring sheet's going to be on Monday.